Some problems just don't solve easily in a Cartesian system or the normal tangential system. And so in those situations, we'll have to go to a polar coordinate system. Or as our first example will show, we'll actually use a combination of the two. But one thing we need to keep in mind is that when we're in the polar force system, Newton's second law still holds true, but the acceleration is not just a single term. So the radial component of the acceleration is r double dot minus r theta dot squared. This is to say there's a component of the acceleration radially outward, speeding up or slowing down, so it could be inward. And then if there's a rotation taking place, there's a centripetal portion of the acceleration. Then we also have the transverse component, r theta double dot, you might recall, if you're on a merry-go-round, and you're on your horse here, as the merry-go-round speeds up, and you're moving faster and faster in this circle, that's r theta double dot. That's your speeding up, or as the merry-go-round stops, that's your slowing down. If your radius is not constant, there's still going to be a component perpendicular to the radius, and that's going to be 2r dot theta dot, sometimes looked at as the Coriolis effect. But the point is that there's two terms in the radial acceleration, there's two terms in the transverse acceleration. So here's a problem, and this problem looks like it might easily solve in the xy system. And in fact, we'll use xy. But one of the things we have to keep in mind is that as block A moves forward, block B is going to fall. But the rate at which block A moves forward, either the velocity or the acceleration, is not equal to the rate at which block B falls. And that's because of this angle theta, which is the same as that angle theta. And one of the things we keep in mind here is that as the block A is moving, theta is changing. And that's why these two accelerations are not the same. And so this system really wants to be solved with a radial transverse actually in conjunction with an xy system. So as I look at this system, something very interesting is going to take place. If I place the origin for the A block here, and the radial is in that direction. So here's E radial as I draw it down here on block A. And then E transverse is perpendicular to that. As I look at block B, E radial is straight down. So there's E radial. E transverse is to the right. I'm really not going to use that because nothing is happening with block B to the right. So I need to take advantage of that. I can see that block A is going to be moving to the right. So the acceleration of A is to the right. Acceleration of B is straight down. But if I want to look at a constraint based on this piece of string or this cord, then the length of the cord is equal to r sub A plus r sub B, where here's r sub A and this distance is r sub B. So as I look at the first derivative with respect to time, L dt is equal to 0, that's going to equal r sub A dot plus r sub B dot, where r sub B is the velocity of B, but r sub A is the movement in this direction. That's not exactly the same as the velocity of A. But we're more interested in the next derivative, still 0 on the left side of the equal sign. And this would be r sub A double dot plus r sub B double dot. And so r sub A double dot equals minus r sub B double dot. So now we're ready to draw some force diagrams and set up some force equations. So when I look at the forces on A, I have the weight of A, which is 40 pounds. So that's gravitational force due to the Earth acting on block A. There's a tension in this direction, T. That's a tension due to the cord acting on block A. So there's a normal force due to the surface acting on block A. Then as I look at the forces on B, I have the weight of B, that's gravity due to the Earth acting on block B, and there's a tension up, and since the cable is light and the pulley is massless and frictionless, this tension and this tension are the same. So that's a tension due to the cord acting on block B. Now when I draw the force equations For block A, I'm going to want to use a Cartesian system, interestingly enough. And so my x direction is your standard x, and my y direction is here. And by alternate interior angles, that's theta. For block B, I'm still going to stick with the radial direction. And notice positive is down, so I'm going to take advantage of that. So the sum of the forces in the x direction, I get t cosine theta equals the mass of A times the acceleration of A. Now the acceleration of A is strictly in this direction, strictly in the horizontal or x direction. In the y direction, I get the sum of the forces in the y. That's going to be the normal force plus t sine theta minus WA, and that's going to equal 0. For block B, I have WB. Remember, that's in the positive radial direction, so this is the sum of the forces in the radial direction, minus the tension equals m sub b times a sub b. Now, a sub b is, in fact, r sub b double dot. Right? There's no r sub b theta sub b dot squared. That term is going to go to 0 because there is no change in the angle. For this case, that angle would be in here. There is no angle. It's 0 degrees, and it's going to stay 0 degrees. Well, I can solve this equation for tension. The tension equals W sub b minus m sub b, r sub b, double dot. And I'm going to substitute that tension into this equation. And so I get WB minus m sub b, r sub b, double dot, times the cosine of theta equals m sub a sub a. Now keep in mind, there is a relationship between r sub b double dot and r sub a double dot. But this is not r sub a double dot. R sub a double dot is going to be up and to the right. Acceleration of a is in this direction. So there's going to be a component of that acceleration along the radial direction and a component along the transverse direction. So here's a sub a. This is the angle theta still, the 30 degrees we had before. And so this side is r sub a double dot minus r sub a theta dot squared. I actually have to put in a minus sign here because remember, E subradial is in this direction, down and to the left, but that acceleration is pointing up and to the right. For this particular example, theta dot is equal to 0. How do I know that? Going back to the original problem, the two blocks are released from rest. And so since everything is just beginning to move, all velocities are 0. It's kind of like dropping a ball. As soon as you let go, it starts moving. But that initial velocity is still 0. Same thing holds true for this angle. It's at 30 degrees, and it's initially not changing. It's going to immediately begin to change, but initially it's not changing. So taking advantage of that, that means, since theta dot is 0, minus r sub a double dot equals a sub a cosine of theta. But r sub a double dot is minus r sub b double dot, or r sub b double dot is minus r sub a double dot. And so I can put a minus r sub a double dot in here. So when I do that, that minus sign is going to change that to a plus. So I'm going to get w sub b plus m sub b r sub a double dot times the cosine of theta equals m sub a sub a. But r sub a double dot is minus a sub a cosine theta. So this becomes w sub b cosine theta minus m sub b a sub a cosine theta. That's just this term right here, times another cosine theta, that's from right there, equals m sub a sub a. Or WB cosine theta equals m sub a sub a plus m sub b cosine squared theta a sub a, which is a sub a times m sub a plus m sub b cosine squared theta. And so a sub a equals W sub b cosine theta all over m sub a plus m sub b cosine squared theta. If I multiply numerator and denominator by g, I get WB cosine theta g over WA plus WB cosine squared theta. WB is 50 pounds, cosine 30 degrees, g is 32.17 feet per second squared. Denominator is W sub A, which is 40 pounds, plus WB, which is 50 pounds, cosine squared 30 degrees. Notice the pounds in the numerator will cancel the pounds in the denominator, and my only unit left over is feet per second squared, which is an acceleration, so that all works out very nicely. And I get 17.97 feet per second squared for the acceleration of block A. So that's the initial acceleration of block A. So now if I want to solve for the tension, I know that the tension equals m sub A sub A over the cosine of theta. Tension equals 40 pounds over g times 17.97 feet per second squared times the cosine of 30 degrees, which is 19.35. G is in feet per second squared, so those units would cancel. And then finally, the acceleration of B is equal to minus the acceleration of A, minus this minus that. The acceleration of B then is A sub A cosine theta. That's 17.97 feet per second squared times the cosine of 30 degrees, which is 15.57 feet per second squared. Now I just want to quickly address this last part. Repeat if the velocity of block A is 6 feet per second squared. The main thing there is I now have a velocity for A in this direction of 6 feet per second squared, which means there's a velocity in that direction and a velocity in this direction. Now if you go back to velocity, the vector quantity in the polar system, this is r dot times E radial plus r theta dot times E transverse. The important thing here is that this is r theta dot. And so if this is 6 feet per second, and this is the angle theta, then r theta dot equals 6 feet per second times the sine of 30 degrees. Theta dot is no longer 0. And so when I do all of those acceleration calculations that I did earlier, this term is not 0, but I can solve for it because I know that r is equal to 2.4 feet. So in that scenario, theta dot equals 6 feet per second times the sine of 30 degrees, which is a half, all over 2.4 feet, which is 1.25 seconds to the minus 1. Notice you have feet per second in the numerator, feet in the denominator. That's going to be inverse seconds, or radians per second.